This is the lecture for BMFG 1213 Engineering Materials, the continuation of Chapter 12A Functional Properties of Materials, Electrical Conduction and Semiconductivity. We already covered the first part, which is electrical conduction, and for this lecture we're gonna continue with semiconductivity properties. So, in this lecture, we will discuss more about the electron excitation events that produce free electrons and holes in metals, semiconductors, and insulators. Define intrinsic and extrinsic semiconductors and how charge is transported in such material. 12.2 Semiconductivity. Semiconductor material. Semiconductors are materials that have electrical conductivities between highly conducting metals and poorly conducting insulators. Two general classifications of semiconductors are the elemental semiconductor materials found in group 4A of the periodic table and the compound semiconductor materials. Most are formed from combination of group 3 and group 5 elements. So this is the example for elemental semiconductor such as silicon. Germanium is coming from group 4A, while for compound semiconductors is combination of group 3 and group 5 elements. Such as aluminum is coming from group 3, phosphide is coming from group 5. So we combine those aluminum and also phosphorus. You got aluminum phosphide, aluminum arsenide, gallium phosphide, gallium arsenide, and indium phosphide. Hence, semiconductors can be divided or classified into two main classifications. The first one is intrinsic. Second one is extrinsic. Intrinsic semiconductors chemically very pure and possess poor conductivity. It has equal numbers of negative charge carriers and positive charge carriers. Small current flow by thermal agitation. So for intrinsic, the electron equal to the hole. For extrinsic, small amount of impurities added by a process known as doping. Numbers of negative carriers, electrons, and positive carriers, holes are not equal. So doping gives rise to negative charge conductor N-type semiconductor or positive charge conductor P-type semiconductor. So for extrinsic, we must have a dope material to give rise to either negative charge to have N-type or positive charge to have P-type semiconductor. Elemental or intrinsic semiconductors. Pure elemental silicon and germanium are intrinsic semiconducting materials. These elements, which are in the group 4A, have a diamond cubic structure with highly directional covalent bonds. In this structure, each silicon or germanium atom contributes 4 valence electrons. This is the figure of atomic structure of silicon. We can see that the silicon have 4 valence electron, 1, 2, 3, and 4. Similar with germanium, also have 4 valence electron. The bonding in semiconductors is predominantly covalent and relatively weak. The valence electrons are not as strongly bound to the atoms. Elemental intrinsic semiconductors. This is the crystal lattice for silicon. We can see in here the silicon share the valence electron to have a stable arrangement. It share the unique capability of semiconductor atoms is their ability to link together to form a physical structure called a crystal lattice. The atoms link together with one another sharing their outer electrons. These links are called covalent bonds. We can see that silicon only have 4 valence electrons, but it shares each electron with each other to have a stable condition. The sharing of electron, we call it as covalent bonds. Consider nominally pure semiconductor at T equal to 0 Kelvin. There is no electrons in the conduction band. So the conduction band at T is 0 Kelvin, is empty, and also the valence band is filled with fully with electron, and we can have in here the energy gap between the conduction and valence band. At T above 0 Kelvin, a small fraction of electrons is thermally excited into the conduction band, leaving the same number of holes in the valence band. So at T above 0 Kelvin, uh, the electron from valence band will jump or excite into the conduction band. So it will leave the holes in the valence band. When an electric field is applied, a force is exerted on the valence electrons of atom B. It will move to the vacancy in atom A. So once the electron jumps into the conduction band, we can have a hole in here, a hole in here. And next, when we apply the electric field, the uh, the next or the nearest electron will fill up the hole, and the process will continuously occur whenever the electric field is applied. So a hole will now appear at atom B, and in effect it have moved from A to B in the direction of the applied field. So we can see in here the applied field is down below. So the hole is moving by the direction of electric field, but the electron is moving opposite to the direction. You can see we start with A. From A, there is a hole in here. After that, the electron fill in the hole. So they will develop a new hole in here, and then the nearest electron will fill up the hole in here, and then the process will continuously occur. When a sufficient amount of energy is supplied to a valence electron to excite it away from its bonding position, it becomes a free conduction electron and leaves behind a positively charged hole in the crystal lattice. In the electrical conduction process in the semiconductor such as pure silicon, both electrons and holes act as charge carriers and move in an applied electric field. Conduction electrons have a negative charge and are attracted to the positive terminal of an electrical circuit. Holes, on the other hand, behave like positive charge and are attracted to the negative terminal of an electrical circuit. A hole has a positive charge equal in the magnitude to the electron charge. So the electron will attract to the positive terminal while the hole will attract to the negative terminal. Semiconducting electron and hole. For intrinsic semiconductors at temperature above 0 Kelvin or absolute zero, the electrons and holes contribute to the current when a voltage is applied. For intrinsic, both electrons and holes will contribute to the current when a voltage is applied. Electron conduction is easy to imagine. Electrons in the conduction band move almost like free particles. So we can have a see in this figure the electrons from valence band will excite into the conduction band, so it will conduct electricity and will left a hole in the valence band. Simultaneously, the hole also will move this way, and also while the electron move this direction. Hole conduction is due to positively charged particles in the valence band. During electrical conduction in intrinsic semiconductors, the current density J is equal to the sum of the conduction due to both electrons and holes. By using this formula, we can determine the current density J. J equal to NQVN plus PQVP. N is the number of conduction electrons per unit volume. P is the number of conduction holes per unit volume. Q, absolute value of electron or hole charge. This is the constant. Vn or Vp, drift velocities of electrons and holes respectively. Dividing both sides by the electric field E and using J equal to sigma E, we can have this kind of equation. So electrical conductivity sigma equal to current density over electric field. Then we divide both with E, then we can get that the electrical conductivity of semiconductors equal to NQ mu N plus PQ mu P. Vn over E and Vp over E are called the electron and hole mobilities respectively, or we can write it in this symbol mu N and mu P. So mu N is Vn over E, while mu P Vp over E. Well, mu is mobilities. In intrinsic elemental semiconductors, N equal to P equal to Ni. So for this, the intrinsic elemental semiconductor, N or electron equal to the hole. So we can conclude that the charge carrier is Ni. Ni is intrinsic carrier concentration. So from this equation we can simplify it into this final equation, which is sigma equal to Niq multiplied by mu n plus mu p. Doping. What is doping? Semiconductors can be easily doped. Doping is the incorporation of impurities into a pure crystal semiconductor according to certain requirements, which change drastically the electrical properties of semiconductor materials. Impurities such as atoms of the elements differ from those forming solid. Interstitial foreign atoms squeeze between the regular sites, crystal sites, substitute foreign atoms occupying the site of host atoms. So you already know about this term interstitial and substitute. So in doping, we can have these two situations. The first one is interstitial, where the atoms squeeze between the regular sites, crystal sites, while substitute, the foreign atoms occupy or replace the sites of host atoms. Why doping is important? Doping is very important when we discuss about the extrinsic semiconductors. Extrinsic, extrinsic semiconductors are very diluted substitutional solid solutions in which the solute impurity atoms have different valence characteristics from the solvent atomic lattice. The process of adding small amounts of substitutional impurity atoms to silicon to produce extrinsic silicon semiconducting material is called doping, while impurity atoms themselves are called dopants. The concentrations of the added impurity atoms in these semiconductors are usually in the range of 100 to 1000 parts per million. So that one is very small. The portion, the addition or the doping quotient is very small. We can see in here in this figure, silicon has 4 valence electrons. Then we dope with phosphorus, where phosphorus have the is coming from the fifth group elements of periodic table, so it has extra atom in here. So by doping the phosphorus, we can have the extra electron, or we can have N-type semiconductor. While by doping this boron is coming from group 3, so it's lack of one electron. So by combining this boron with silicon, we can have the hole in here. So when we have a hole, we call it a P-type semiconductor. Phosphorus is coming from group 5, while boron is coming from group 3. Group 5 have excess electron, while boron have lack of electron, so it have a hole. Excess electron, we call it N-type semiconductor, while the hole, or by doping a hole, we call it P-type semiconductor. N-type extrinsic semiconductors. If an impurity atom of group 5A element such as phosphorus or arsenide replace a silicon atom which is a group 4A element, there will be one excess electron above the 4 needed for the tetrahedral covalent bonding in the silicon lattice. What happens with the remaining electron? The extra electron is only loosely bonded to the positively charged phosphorus nucleus and has a binding energy of 0.044 electron volt at 27 degrees C. It can be easily ionized. So this kind of electron can be easily ionized or can be easily excited into the conduction band. This energy is about 5% of that required for a conduction electron to jump the energy gap of 1.1 electron volt of pure silicon. In other words, only 0.044 electron volt of energy is required to remove the excess electron from its parent nucleus so that it can participate in electrical conduction. When under the action of an electrical field, the extra electron becomes a free electron available for conduction, and the remaining phosphorus atom becomes ionized and acquires a positive charge as shown in figure B. So this is the figure where we add a element from the group 5A. For this example, we choose a phosphorus in here. Phosphorus have extra or excess of electron in here, one electron. Suppose this electron, when we apply the electric field, will easily becomes a free electron. So it will jump into the conduction band to conduct electricity. That is what we call N-type extrinsic semiconductor. When impurity atoms from group 5A such as phosphorus, arsenide, antimony are added to silicon or germanium, they provide easily ionized electrons for electrical conduction. They are called donor atoms. Silicon or germanium semiconductors containing group 5 impurity atoms are called N-type or negative type extrinsic semiconductors since the majority charge carriers are electrons. The band structure view. In terms of the energy band diagram for silicon, the extra electron of group 5A impurity atom create an energy level, shallow level within the band gap close to the conduction band. The electrons occupy an energy level in the forbidden energy gap just slightly below the empty conduction band. Such an energy level is called a donor level ED since it is provided by a donor impurity atom. The energy required to ionize the atom is small and a sizable fraction of donor atoms will be ionized at room temperature. If we can observe in this figure, we can see in here there are full valence band, empty conduction band, and also the energy band gap. In here, when we add donor atoms or the impurity from group 5, there will create a new energy level. We call it energy donor level or ED, which is much smaller compared to EG. There in here we can see the electron, the excess electron or the freely moved electron can easily excited to the conduction band to conduct electricity because the energy gap is much smaller compared to the EG in here. So A donor is similar to a hydrogen atom, a positive charge with a single electron within its potential. Such impurities are called hydrogenic donors. Okay, this is the another case of N-type semiconductor. This one, the silicon was doped with arsenide, As plus in here. So similar to the phosphorus, the arsenide also have a excess electron in here. The excess electron will create the donor level at the uh, just below the conduction band. So we can see in here the gap is shallow compared to the original energy band gap. There will be excess electron in here ready to be excited at T equal to 0 Kelvin. When the temperature was increased above 0 Kelvin, the electron will start to excited into the conduction band. We can see in here the previous electron have been excited to the conduction band, and also this electron have been excited to conduction band to conduct the electricity. Because due to the shallow energy of the created by the donor atom in here. Then we move to the another type of extrinsic semiconductors, which is P-type extrinsic semiconductors. When a trivalent group 3A element atom, example aluminum or indium or boron, is substitutionally introduced in the silicon lattice in the group 4, one of the bonding orbitals is missing and a hole exists in the bonding structure of the silicon. At T equal to 0 Kelvin, this hole stays with atom localized hole. If an external electric field is applied to the silicon crystal at T above absolute zero temperature, electron from the neighboring silicon atom attain sufficient energy to break loose from its bond and jump or move into the hole of the boron atom. The hole can then migrate and contribute to the current. When an electron from neighboring silicon atom fills the hole associated with the boron atom becomes ionized and acquires a negative charge of -1. Okay, in here, the silicon has been doped with boron, while boron lack or missing one electron at their valence orbits. So it will create one hole in here while, while we apply the electric field, the nearest or the nearest electron, silicon uh, valence electron will fill up the hole, and it will create another hole at the silicon. This process will continuously occur, then it will conduct the electricity. The binding energy associated with the removal of an electron from silicon atom, thereby creating a hole, and the subsequent transfer of the electron to the boron atom is only 0.045 electron volt. This amount is smaller compared to the 1.1 electron volt required to transfer an electron from the valence band to the conduction band. The presence of electric field, the hole behaves as positive charge carrier and moves in the silicon lattice toward the negative terminal. In terms of the energy band diagram, the impurity atoms such as boron or aluminum provides an energy level called an acceptor level that is slightly higher, around 0.045 electron volt, than the uppermost level of the full valence band of silicon. When the valence electron of a silicon atom near a boron atom fills a missing electron hole in a boron-silicon valence bond, this electron is elevated to the acceptor level and creates a negative boron ion. Atoms of group 3A elements such as boron, aluminum, and gallium are called acceptor atoms as they provide acceptor levels in silicon semiconductors. Since the majority carriers in these extrinsic semiconductors are holes in the valence bond structure, they are called P-type or positive carrier type extrinsic semiconductors. If we focus on this figure, we can see that there are full valence bands in here, empty conduction band, and also the original energy band gap. So by doping with the group 3 elements such as boron, aluminum, and gallium, it will create a acceptor level so that the acceptor level is slightly higher than the uppermost level of the full valence of silicon. Is just higher than the full valence band of silicon. So, but the band gap or the gap between the acceptor level and the valence band is just a shallow gap in here. Shallow gap around 0.045 electron volt. So, uh, when the electric field is applied, the at T much higher than 0 Kelvin, uh, there is a hole in here provided by boron, aluminum, and gallium, and then the electron from the full valence band will fulfill the missing electron or fulfill the hole, so it will create another hole in here. So this process will continuously occur. So it will create it will conduct the electricity by the movement of hole in here. It will create another hole, hole by hole by holes. So this kind of movement, we call it a P type of positive carrier type extrinsic semiconductors. And also in here we have another type or another kind of P types extrinsic semiconductors such as silicon doped with aluminum. As we know, aluminum is coming from the group 3A, which is lack of or missing of one electron at the valence band. So the excess or the missing electron will create the hole in here. At T0 Kelvin, it will create the acceptor level uh, in here in the empty space of energy band gap, just slightly higher than the valence band, but with the narrow gap, and the hole will reside in here at T above than 0 Kelvin, the electron from the valence band will easily to excite to fulfill the hole, and hence it will create another hole in the valence band, and the process will keep continue, so that this kind of semiconductors will conduct the electricity by using the holes, or we call it p type semiconductor. P-type versus N-type semiconductor. There are a few differences between the P-type and N-type semiconductor. For P-type semiconductor, the doping element have a missing electron or a hole in here. Compared to the N-type doping element have extra electron in here. So another difference is, for the P-type, it will create the acceptor level just above the valence band, while for N-type, it will create the donor level just below the conduction band. And for acceptor level, for P-type semiconductor, in the acceptor level, it will have a hole in the acceptor level, and for N-type, it have excess electron in the uh, donor level in here. So for P-type, the electron from valence will excite to the acceptor level to fulfill the hole, while for N-type, the excess electron will excite to conduction band, hence will create the hole in here. So that one is that there are the few differences between P-type and N-type semiconductor. Effect of doping on carrier concentration. In semiconductors such as silicon and germanium, mobile electrons and holes are constantly being generated and recombined. The product of the negative free electron and positive hole concentrations is a constant. Uh, by using this formula, we can calculate the charge carrier Np equal to Ni squared, where Ni is the intrinsic concentration of carrier in a semiconductor, is a constant at a given temperature. This relation is valid for both intrinsic and extrinsic semiconductors. The concentration of electrons in in an N-type semiconductor is referred by Nn, majority carriers. For N-type, Nn, and that of holes in N-type by Pn, minority carriers. Nn is majority carriers, Pn is minority carriers for N-type. And in here, you got N in here. There are two types of charged particles in extrinsic semiconductors. The first one is immobile ions. The second one is mobile charge carriers. Nd, the concentration of the immobile positive donor ions. Na, the concentration of the immobile negative acceptor ions. And N, the concentration of the mobile negative charge carriers representing electrons, while P, the concentration of the mobile positive charge carriers representing holes. Since the semiconductor must be electrically neutral, in N-type semiconductor, Na will be 0 or equal to 0. Since the number of electrons is much greater than the number of holes in an N-type semiconductor, that is, N must be greatly greater than P. So we can have in here, uh, in N-type semiconductor, the free electron concentration is approximately equal to the concentration of donor atoms. Or we can have in here N free electron concentration in N-type is approximately equal to the concentration of donor atoms. Using Np equal to Ni square, the concentration of holes in N-type semiconductor is given as Pn equal to Ni square over N, or approximately equal to Ni square over Nd. For example, in this case, a silicon wafer is doped with 10 to the power of 22 phosphorus atoms per meter cube. Then you need to compute first one, majority carrier concentration. Then you need to calculate the minority carrier concentration. Finally, you need to calculate the electrical resistivity of doped silicon at room temperature. So the first solution, you need to calculate the majority carrier by using this formula. Majority carrier but first you need to know what type of semiconductor is this. Phosphorus is the fifth uh, group element, so it will dope in the silicon wafer. So this is N-type semiconductor. And for N-type, the Nn equal to Nd, so your N majority carrier concentration is equal to 10 to the power of 22 electrons per meter cube. Then you need to calculate the minority carrier concentration, which is the P. Majority is N, while for the minority carrier concentration, which is P or holes, Pn equal to Ni square over Nd. You just insert the value in this equation, then you can find that the whole carrier concentration is about 2.25 multiplied by 10 to the power of 10 holes per meter cube. Finally, you need to calculate the electrical resistivity, 1 over Q mu n Nn. And then you just insert all the value in this equation. In here, finally, you got the electrical resistivity of this N-type semiconductor. Okay, semiconductor devices, the p-n junction diode. A p-n junction diode can be produced by growing a single crystal of intrinsic silicon and doping it with N-type. First, you need to doping with N-type material. Then you dope with P-type material. First, you need to dope with N-type. The next step is dope with P-type material. More commonly, the P-N junction is produced by solid-state diffusion of one type of impurity such as P-type into existing N-type material. Some applications for PN junction diode are rectifier diodes and breakdown diodes. This is the example of the real application of PN junction rectifier diodes, converting and alternating current AC to direct current. Firstly, consider an ideal case in which P-type and N-type silicon semiconductors are joined together to form a junction. In the N-type, the electrons are the charge carriers, while for p-type the holes are the majority charge carriers. So by combining these two type of semiconductors, n-type and p-type, the majority carriers near at the junction diffuse across the junction and recombine. So electrons we will recombine with the holes at the junction. Since the remaining ions near or at the junctions are physically larger and heavier than the electrons and holes, they remain in their position in the silicon lattice. So the ions, positive and negative, remains at their position in silicon lattice because it is physically larger and heavier. Semiconductor devices, the PN junction diode, after a few recombination of majority carriers at the junction, the process stops because the electrons crossing over the junction into the p-type material are repelled by the large negative ions. Similarly, holes crossing over the junction are repelled by the large positive ions in the n-type material. The immobile ions at the junction create a zone depleted of majority carriers called depletion region. Under equilibrium condition, such as open circuit condition, there exists a potential difference or barrier to majority carrier flow. Thus, there is no net current flow under open circuit condition. So after a few moments, the recombination of the electron from n-type to p-type, while hole at from p-type to n-type will stop because the carriers were repelled by the ions in respective region. So the immobile ions at the junction create a zone, then it will create a zone in here. The zone is called depletion region. Under equilibrium condition, there is a potential difference or barrier to majority carrier flow. Thus, there is no net current flow under open circuit condition. Okay. When an external voltage from battery is applied to a PN junction, it is said to be a bias. The PN junction in here is said to be a reverse bias. If the n-type material of the junction is connected to the positive terminal, n-type to the positive terminal, while p-type to the negative terminal. With this arrangement, the electron from n-type will attracted to the positive terminal, while the holes from the p-type will attracted to negative terminal. Both are away from the junction in here. So what happened next? The movement of the majority carrier electrons and holes away from the junction increase its barrier. So the barrier will become larger, and increase its barrier width. This is the barrier width. As a result, current resulting from majority carriers will not flow. In reverse bias mode, thermally generated minority carriers, holes in n-type and electrons in p-type material will be driven toward the junction so that they can combine and create a very small current flow under reverse bias condition. This minority or leakage current is usually of the order of microampere. So what happened in here? The minority carriers will attract to each other at the junction and thus will create a very small current flow under reverse bias condition, and this minority or leakage current is usually of the order of microampere. The PN junction diode is said to be a forward bias if the N-type material of the junction is connected to the negative terminal of an external battery, while the P-type is connected to the positive terminal of the external battery. In this arrangement, the majority carriers are repelled toward the junction. So for N-type, the majority carrier of electrons will flow toward the junction and enter the P-type, while the holes from P-type will flow toward the junction and enter the N-type. During the forward biasing of a PN junction, electrons from battery enter the negative material of the diode. So during this process, the electron from the external battery will enter the negative terminal of the diode or the PN junction. So it will supply the electron to continuously recombine with the hole. Electron flow can continue as long as the PN junction is forward biased and the battery provides an electron source. Examples. Explain with the help of illustration the change occurred in single crystal silicon semiconductor when added with phosphorus atoms. Phosphorus is the group 5 impurity. Compare the energy band diagram for metal, semiconductor, and insulator with the help of illustration. Indicate their valence band gap, if any, and conduction band in your illustration. So this is the answer for the example. Example A. It is better if you can illustrate your answer by using a figure to ease your understanding and also to ease the reader's understanding. You can draw this kind of illustration. The silicon you dope with phosphorus. Phosphorus have the excess or addition electron which can freely move during applied electric field, and then you can explain step by step. And also this is the answer for the example B. You can draw first the energy band gap of conductor. This one is at 0 Kelvin. This one is for conductor at temperature above 0 Kelvin. This one is for insulator, and then the last one is for semiconductor. And you need to explain each figure so that you can obtain full mark for this kind of question. And the summary. The ease with which a material is capable of transmitting an electric current is expressed in terms of electrical conductivity, or its opposite, resistivity. On the basis of conductivity, a material may be classified as conductor, semiconductor, and insulator. In the energy band model, the valence electron of the metal atoms interact to form energy bands. Energy bands of the valence electron of metal atoms overlap. For metal atoms is overlap. Very little energy is required to excite the highest energy electrons so that they become free to be conductive. For intrinsic semiconductors have a relatively small energy gap between their valence and conduction bands. By doping the intrinsic semiconductors with impurity atoms to make them extrinsic, the amount of energy required to cause semiconductors to be conductive is greatly reduced. Extrinsic semiconductors can be N-type or P-type. The N-type, which is negative, semiconductor have the electrons for their majority carriers, while for the P-type have the holes or the missing electrons for their majority carrier. So that is all about chapter 12a. Thank you for your time. Assalamualaikum warahmatullahi wabarakatuh and good day.